Okay, folks, so right back at it. So I felt that last video getting a little long. I've been trying to record shorter videos for my other class. My PChem students told me they like shorter videos, so I cut that last one off kind of abruptly because I felt it was going a little long. So let's just pick right back up, okay? So more heat capacity calculations, okay? So let's do another sample problem. So a 30 milliliter sample of water at 280 Kelvin is mixed with a 50 milliliter sample of water at 330 Kelvin. Calculate the final temperature of the mixture, assuming no heat loss to the surroundings. So this is exactly what I told you we were going to do, like at the very first lecture I recorded. You have a cold object, hot object. What happens when we mix them? Can we predict the final temperature? And we can, okay? And here's how we're going to do it, okay? First of all, we're going to recognize, so one thing I'm going to tell you, a couple tips here. So again, when I have a hot object in contact or mixing with a cold object, heat will flow from the hot object to the cold object, okay? So what that means is if we look at the heat, the Q of the hot object, so the heat delivered to the hot object has to be the heat absorbed by the cold object, right? Because if we're assuming there's no heat loss to the surroundings, that's kind of like saying this whole thing is like in an isolated container, okay? So the heat from the hot object has to be the heat delivered to the cold object, and specifically we have to say negative Q hot equals positive Q cold. This is going to be really important for this calculation to get it right. So if heat is leaving the hot object, right, then as viewed by the hot object, that's negative. And if heat is entering the cold object, then as viewed by the cold object, that's positive. So this is something that's good to kind of commit to memory. When you have objects in contact, negative Q hot equals positive Q cold, okay? And so from there we can, and then the other thing I'll tell you, right, because this is 30 mils of water, I should have given you this in the problem, but we'll assume that water is 1 gram per milliliter, right? So that should have said that in the problem, but it didn't. So if we have negative Q hot equals positive Q cold, and I've got mass here in the form of density from my volume, then what I'm going to do is say now this, I know that Q equals M times CS times delta T, and there's a negative, so that's for the hot object. And now for the cold object, that's going to be an M times a CS, also times a delta T, okay? And of course, there's a positive sign in front of there. And so now, if I start plugging away here and recognizing if I'm assuming 1 gram per milliliter, then I'm just going to replace this with this 30 milliliters is going to become 30.0 grams, and this 50 milliliters is going to become 50.0 grams, okay? So let's see here. The 50 grams was the hot stuff, so we're going to plug and chug away. I'm going to say 50.0 grams. The heat capacity of water, so I looked up a better value. I also didn't give that to you there. So CS of water, I know we calculated it before, but it's actually 4.184 joule per gram per degree C is the experimental value. So there's two things I forgot to give you in this problem. So if you're freaking out, like, how do I do this problem? So keep in mind, you would have had to have the heat capacity and the density, which you could have looked up as well, okay? And so now what am I solving for? Calculate the final temperature. So in this delta T, that's going to be TF minus, but now I have to get the initial temperature right. And so for the 50 grams of water, that initial temperature was 330 Kelvin. And now because that's Kelvin, I'm going to recognize that I can write this unit as joule per gram per Kelvin. It's the same thing as joule per gram per degree C. Okay, and so now all of that equals positive. So I put a parenthesis there and a parenthesis there. Okay, and then so that's 30 grams, and it's still 4.184 joule per gram per Kelvin. And then now it's still TF, and we recognize that this TF and this TF are going to be the same. That's the quantity that I'm solving for. And so because it's delta T, it's temperature final minus temperature initial, and the cold water was initially at 280 Kelvin. So now I've got my equation set up, and it looks kind of like a monster. But all I have to do now is solve for T final. And there's a couple simplifying tricks I can do. I recognize that the heat capacity is the same on either side. Actually, let's make this so that we can tell what I'm doing here. Okay, so I'm going to cancel this and I'm going to cancel this because they're the same. And then now what I'm going to do is try to isolate my T finals. And I'm going to do that by dividing both sides by 30 grams. So divide this side by 30 grams and divide this side by 30 grams. And that cancels that. And so 50, let's do this, 50 divided by 30 equals 1.67 with three sig figs. So now that's 1.67, and there's still that negative sign there. Don't forget about that negative sign, okay? So now that's negative 1.67. Remember, I canceled the heat capacities. So all that's left is T final minus 330 Kelvin. And that's a 330 point up there, right? So 3 sig figs. And now that equals, and okay, so I divided by 30 and I canceled that. So the only thing I have left on this side is T final minus 280. We'll say there should have been a decimal point there for 3 sig figs as well. Okay. TF minus 280. And so as you can see now, this isn't so bad. So I'm going to distribute this number through. So that's negative 1.67 TF minus, and then when I say negative 1.67 times 330 negative, there's a negative sign there, I get 550, okay? Positive. All right? And I'm going to drop the units here during my algebra, but I know that the units are going to work out to be Kelvin. Okay? And so now that's still T final minus 280. And so now I've got to solve for TF. And I'm going to do that by, let's see here. So I can add the 280 over to this side to cancel that. So plus 280. And plus 280. Okay, so 550 plus 280 equals 830. So now my equation says 830 on this side, and then what I'm also going to do, two steps at once, I'm going to say plus 1.67 TF and plus 1.67 TF on this side. Sorry, my algebra is getting a little sloppy. So now, when I add 1.67 TF to TF, that gets to be 2.67 TF. And then finally, TF is 830 divided by 2.67. And that equals 310. With three significant figures, we'll say that's 311 Kelvin. And if you think about it, that makes good sense because the 30 grams of water was at 280 and the 50 grams of water was at 330. So that's about like halfway between, considering that they're not the same mass. Awesome. So as you can see, this problem got pretty complicated. with the algebra, but we started with this idea of saying negative Q hot equals positive Q cold. Okay? So anytime we're going to do a problem where we have a cold object in contact with a hot object, this is what we want to remember. Negative Q hot equals positive Q cold. Okay, so let's move on. And so obviously this is a physical transition.